Hey guys, in this one we're looking at our final type of graph transformation, at least for now. So this is stretches and squashes along the x-axis. So hopefully you've watched the reflections video and you've watched the first stretching video where we were stretching vertically or squashing vertically along the y-axis. That comes from when we multiply the function by some number a, stretches and squashes horizontally along the x-axis happen when we multiply the x in the function by some number a. Now a can be positive or negative. We're just not going to be looking at a equals 0 or a equals 1 because otherwise we would just have f of 0 or f of x. So there would be no transformation. Okay, so as always when we're dealing with transforming the x part of a function instead of the function itself, things get a little bit counterintuitive. So what happens when we multiply the x term in the function? The y values, so the y-intercept, the y-coordinates of maximums and minimums stay the same. The x-coordinates, if we transform to f of a of x, then the x-coordinates are multiplied by 1 over a. So instead of when we were transforming the whole function, so multiplying a function by this number a, y values were multiplied by a. When we're dealing with x, if we have f of a of x, x values are multiplied by 1 over a. So as always with x, it's a bit counterintuitive. So if a is greater than 1, then the graph gets squashed together. So the reason for that is, say for example we had f of 2x, the x values get multiplied by 1 over 2, so 1 half. So x values get squashed in with a scale factor of 1 half. Now what we're going to do first of all, again we're going to transform y equals sine of x, because sine of x is a really good function to illustrate what is going on with these transformations. So the next rule then, if a is less than minus 1, so a is negative, then the graph gets reflected in the y-axis and then squashed together with a scale factor of 1 over a, or you can think of it in full as the x values getting multiplied by minus 1 over a. Now, if a is between minus 1 and 1, then what happens there is the graph gets stretched horizontally along the x-axis, and if a is negative, then the graph gets reflected as well. Okay, so those are our rules. Let's have a look at doing some of these with y equals sine of x and then transforming those. Okay, so hopefully you're all familiar with the sine graph. We'll have a little reminder though just in case. So remember it peaks and troughs at 1 and minus 1 on the on the y-axis, and it cuts the x-axis at 180 and 360 degrees, and every 180 degrees after that. It also goes backwards, so it cuts at minus 180 and minus 360, and every 180 degrees backwards from there. So what we're going to have a look at now is sketching the graph of y equals sine of 2x. Now as with the y stretches, I've already sketched the graphs here because we all know that I can't draw And if I tried to do it live on camera, it just wouldn't go very well. So, we are going to sketch, or have sketched, sine of 2x. So here, a is equal to 2. So the scale factor is 1 over 2, so 1/2. So what's going to happen is it's going to hit the x-axis twice as fast as y equals sine of x. So we still go through the origin at 0. We're going to go through 90 degrees. We're going to go through 180 degrees. We're going to go through 270 degrees. We're also going to go through 360 degrees again. Now back here, we're going to go through minus 90. We're going to go through minus 180 again. We're going to go through minus 270. And we're going to go through minus 360. So hopefully you can see what's going on here. We cut the x-axis twice as many times in the same interval. So let's have a little think about why this happens. So let's say if we draw a table, we got our x value in here, sine of x value in here, and sine of 2x value in here. So when x is 90, sine of x is 1. But sine of 2x, well, that's going to be actually sine of 180. Now sine of 180 is equal to 0. So it's making our sine values happen twice as fast because we are doubling the value of x. Okay, let's look at another one. Okay, for our second example here then, so I've decided to just graph this properly instead of trying to do my ridiculous drawings. So this time we are looking at y equals sine of minus 2x. So this time a is minus 2. So our scale factor is minus 1/2. So what this has done, it's squashed our graph together like the last time when we did sine of 2x, but then it's reflected it in the y-axis. So this is actually a reflection of the guy that we just did. So what's going to happen here then? This point, if you ignore the black writing, this point is 90. This point is 180. This guy is 270. And then this guy again is 360. If we go back over here, we've got minus 90. And we've got minus 180. Then we've got minus 270. And then we've got minus 360. So we've got exactly the same x-intercepts as sine of 2x. But where we would have had maximums, we've now got minimums. Where we would have had minimums, we've now got maximums. So let's also talk about the coordinates of some of these minimums and maximums. So this guy would now be 45 minus 1. This guy would be 135 1, for example. So again, sine of minus 2x has resulted in a squash, so everything is happening twice as fast along the x-axis, but the negative part has then reflected it in the y-axis. Now we're going to take a look at a fractional one. Okay, last one then with the sine curve, so now we're looking at y equals sine of 1/2 x. Now even I could draw this, so it's back to my sketches. So here then, a is 1/2. Now the scale factor is 1 divided by 1/2, which is 2. So what happens here is every x coordinate gets multiplied by 2. So this results in a stretch along the x-axis. The reason for this is everything happens at half the speed along the x-axis. We'll go through a little table in a minute to try and explain that a bit more clearly. Let's label some coordinates. So what we can also see is that whereas we had 2 peaks and 2 troughs with y equals sine of x between minus 360 and positive 360, we only have 1 peak and 1 trough. So our number of peaks and troughs has been halved. So, well, we've still got the intercept over here as 0. Now the next x-intercept is over here again at 360. Now what we're also going to talk about is where the peak happens. So this is at 180 degrees. Now with sine of x, it was at 90 degrees. So the reason this happens is with sine of 1/2 x, well, when x is 180, 1/2 of x is 90. So actually, at 180 degrees, sine of 1/2 of x gets the y value of sine of 90. Sine of 1/2 times 180 is sine of 90. So that's why this slows down, makes us more chilled out. And also back here then, the trough back here did happen on sine of x at minus 90. The trough for sine of 1/2 x is now going to happen, sorry, cock that up. So it's now going to happen here at minus 180. So the coordinates at this point are minus 180 minus 1. And then we've got the same x-intercept over here at 360. So if you're not too sure on why that's happened yet, let's try and explain it in a table again. So let's have sine of x and sine of 1/2 x. So let's have x equals 180. So sine of 180 is 0. Sine of 1/2 of 180 is actually going to give us sine of 90. Now sine of 90 is equal to 1. So sine of 1/2 x when x is 180 is equal to 1. What about when x is 360? Well, again, sine of 360 is equal to 0. Sine of 1/2 of 360 is sine of 1/2, sine of 180. Sine of 180 is also 0. But instead of that giving us our second x-intercept, it's just our first x-intercept after 0 over here. So, fractional values of a slow the graph down. Okay, now we're going to have a look then at quadratics and cubics. First out then, so here we have y equals f of x as a quadratic with x-intercepts -1 and 2, a y-intercept of -2, and a minimum at 1/2 minus 5/4. Now we want to sketch y equals f of 2x. So, for this guy, a then is equal to 2, so the scale factor is 1 over 2. So we simply multiply every important x value by 1/2. So I've already sketched it, but let's put the coordinates in. So this x-intercept on the left, -1, is going to become -1 times 1/2, which is -1/2. This intercept on the right is going to become 2 times 1/2, which is 1, which for some reason is already there. So that's that guy. The y-intercept stays exactly the same, so it's still -2. Y values do not change when you're transforming along the x-axis. And then our minimum, well, the x-coordinate is going to be 1/2 times 1/2, which is 1/4. And then our y-coordinate is still -5/4. So what's happened there then? The graph has been squashed together, the arms of the quadratic are a lot steeper, and the function is thinner. Okay, good times. Okay, second example. So we got the same quadratic. This time we are transforming to f of -1/2 x. So a equals -1/2. So the scale factor is 1 divided by -1/2, which is -2. So again, I've already got the sketch in here. Let's talk about where the coordinates come from. So this guy that was at +2 is gonna change to, or it's gonna get transformed to 2 times -2. So this point gets transformed to this guy over here, which is going to be -4. So remember, because a is negative, we are also reflecting in the y-axis. Now this guy that was at -1 is going to get reflected to -1 times -2, which is +2, which is where this guy comes from. The y-intercept is going to be exactly the same at -2, and then the minimum, the x-coordinate of the minimum, is going to reflect to 1/2 times -2, which is going to give us -1. So this guy has a minimum at -1, and the y-coordinate is exactly the same, -5/4. So we can see what that's done is stretch the quadratic along the x-axis, so it's made the graph fatter or wider, if you like. Okay, good times. Now we're going to look at cubics. So this time then we have a cubic y equals f of x that cuts the x-axis at -1, 1 and 2. It has a maximum at 0, 2, and a minimum at 3/2 -5/8. Now we're going to transform this to y equals f of 1/3 x. So for this then, a is 1/3, so it's a fractional scale factor, so it's a fractional value of a, so it's going to stretch the graph along the x-axis, our scale factor is 1 divided by 1/3, which is equal to 3. So we multiply all of our x-coordinates by 3. So if we start from the left, this guy at -1 becomes 3 times -1, so that gives us -3 for this guy. The maximum isn't going to change. 3 times 0 is just 0, so we have exactly the same point up here, 0, t. This first x-intercept that was a 1 is now going to be a 3 times 1, which is 3. And then this second x-intercept that was a 2 is now going to be a 2 times 3, which is 6. And then the minimum down here, well, the x-coordinate was 3/2, so it's now going to be 9/2, and the y value is still -5/8. So there we have a sketch of our stretched cubic function. Good times. Okay, last example then. Thank God this has taken me about 4 hours. So we got the same cubic and we want to transform it to y equals f of 2x. So this time a is greater than 1. So we're going to squash our graph in. Let's just talk about the scale factor. So a is 2. So the scale factor is 1/2. So we multiply all of our x-coordinates by 1/2. So starting from the left hand, this guy that wasn't -1 is now going to be a -1/2. This guy up here at 0, 2 is still going to be a 0, 2 because 0 times 1/2 is still 0. This guy that was at 1 is now going to be a 1/2. And then this guy that was at 2 is now going to be over here at 1. And then as for the minimum down here, 3/2 times 1/2 is 3/4. So our minimum is now at 3/4 minus 5/8. Like that. So we've squashed our graph together horizontally along the x-axis and get something that looks like that. That's the end of this video. I'm going to go and lie down and cry. Next up we're looking at circles. Hope to see you there. Good times.